everyone. I am Keirsten Nies,
I'm Holden Boone.
I'm Simon Braeger.
and we are doing problem A. It is rating space dust for SCUDEM 10 2025. And we attend the United States Military Academy at West Point. Okay, so introduction to problem A. So space dust primarily is concerned with prebiotic chemistry. So primordial Earth did not have the reduced chemical molecules, methane, ammonia, methyl acetate, etc., required to form life. However, cosmic dust contains the elements necessary to synthesize such molecules in their most basic form. So once these particles enter the atmosphere, depending on size, speed, angle of entry into the atmosphere, the particles are confronted with different types of adversity and manipulation. And once they're on the surface of the Earth, they accumulate in different areas, typically areas of high sedimentation rates like glacial melt holes. And then this congregation of the particles is what makes studying them beneficial to us, because this is where we see higher concentrations of these elements that were required for prebiotic chemistry. So our primary concern is, how does ablation, which reduces particle radius, affect the amount of particles that successfully fall to Earth? So to start the construction of our model, we did a basic falling bodies equation, but we added the addition of a drag coefficient, which is where what you see with our dv over dt base model equation. Our dependent variables were the altitude of the particle at time t, the velocity of the particle at time t, and the radius of the particle at time t. Our independent variable was just time t in seconds after the particle enters the atmosphere. In order to simplify our models, we made the assumption that gravitational force is constant at 9.81 meters per second squared. Each dust particle is spherical. Ablation is uniform. There's no fragmentation or change in shape. Each particle falls straight down at a 90-degree angle and does not experience any lateral movement. This allows us to model the equation with just gravitational force and drag force, so no lateral movement. And then air density depends solely on altitude, so it's an exponential decrease. Then we don't have to model weather equations. So what we did is we took that base model, and A, which in the base model is the cross-sectional area, we made that pi r squared because we are assuming that our particle is circular or spherical. The parameter m, which in the base model is just regular mass, in our adapted model, it's 4/3 pi r cubed times the particle density. And again, this is because we assumed that our particle is always spherical. Our air density, we changed that from a constant to an exponential decrease, and its decrease is dependent on altitude, which is where the EH over H comes from. And then R becomes, we added R into it because now our acceleration is dependent on the radius of the particle. So R becomes its own function, which was modeled in the base models. You saw an equation modeling the rate of change of mass. Here we are concerned more with the rate of change in the radius to better reflect the actual size of the particle changing. Okay, so like I said, our major adjustments account for an air density that decreases exponentially with altitude, and again, the radius of the particle will decrease as it undergoes ablation, therefore size and mass will decrease. And these equations reflect that the change in altitude is dependent on velocity or negative velocity. And then you see our dv over dt, that is the same falling bodies equation, but with our adapted parameters as previously explained, and the same for dr over dt. That base model was dm over dt, but again, we are trying to reflect the change in radius to better account for the change in size of particles.
So to find our parameters for this equation, we used a lot of universal physics parameters, as this is inherently a physics problem, such as gravitational acceleration and atmospheric density at sea level. However, we did have to find some specific ones for our situation. For this, we were able to find a particle density for space dust, which we found from a study. And this gave us 2,000 kilograms per meters cubed. And then also the latent heat of vaporization of the space dust, which we also found a study for. The rest of them were educated guesses, such as the ablation efficiency factor and other sorts of things. We just want to make this simple, and these were some good assumptions to make to simplify the model. Then it came time to actually solve the problem. To do this, we used Mathematica to create graphs and numbers on what actually happens to a single particle, firstly. For this example, we have an initial velocity of 5,000 meters per second, an initial radius of 0.01 meters, pretty standard mid-range sort of value. For this, we're able to show the height is a function of time, the velocity is a function of time, and the radius is a function of time, all very, very valuable. This allowed us actually then to classify different particles, as you can see on this slide. We were able to solve for mini particles by first keeping the height constant at 100 kilometers, which is considered to be the edge of space. And then we varied initial radius and velocity to determine what exactly is the fate of these particles. We defined three possible end states. Firstly, burn up, as defined by the red in this graph, should get trapped in the atmosphere for longer than a day so they don't settle with the other particles, which is a blue color in this graph, and then finally reaching the ground within a day, which is the green color of this graph. As you can see, there's three different functions that both occur for many different particles. This allows us to use this data to see exactly what will happen for a certain particle. We can take pretty much any velocity and radius, and we'll have an accurate idea of exactly how this particle will end up on Earth.
So what this means for us as like a real world interpretation. So 5 to 270 tons of cosmic dust particles enter the atmosphere every day. So this is a greatly substantial amount. And basically what we can use this model to determine is the velocity and average particle radius of a system entering the Earth's atmosphere from the deposited particles in rock strata. And we can then use that model to determine the initial radius velocity pairs that would produce a particle of a certain size, and then use our three outcomes to determine which of these values are valid. Some of the outstanding limitations found in our model, right? So obviously the first one, and probably the biggest one, is that our model does not account for non-vertical trajectories of cosmic dust particles. So you can see this in one of our model equations, which is dH over dt equals negative v. So it's only assuming that all the dust particles that are entering the atmosphere are coming in at an angle that is either vertical or, in other words, like completely perpendicular to our atmosphere. Another one is that our model assumes an exponential atmosphere and does not account for weather in lower atmosphere. So this makes the model less accurate because weather in the lower atmosphere can greatly impact the rate in which dust particles fall to the Earth. Another limitation that we found is that the constant drag coefficient and heat transfer coefficient do not account for things like shape and rotation of cosmic dust particles, right? So like we assumed earlier, we assumed that our cosmic dust particles would be perfectly spherical, and because of that, they would not rotate. The issue with this is that ablation is going to impact those dust particles if they're not perfectly spherical and cause fragmentation.
Okay, thank you for watching. We hope you appreciate our research and our model. We certainly put a lot of time and effort into it.